and he's going to tell us about neural networks.
Yeah. So yeah, thanks. So thanks for coming. I'm Tengyu. I'm at Facebook Area Research for this year as a visiting scientist. I'm joining Stanford afterward. This is joint work based on joint work with Rongo and Jason Lee. Jason is in the audience. For the audience, you may notice that like the first 3 slides actually are borrowed from one of the previous talk I gave here at the same, in the same program, like in one of the previous workshop. But the rest of talk is different, right? So let me start by talking a bit about what I see as some new possible interfaces between users and optimizers in the context of machine learning. So typically, when we talk about optimization, kind of the interface that we have with the users is that the users send the optimization researchers a function f, and optimization researchers, just have to figure out how to solve it, basically. So you can use simple algorithms like gradient descent or local search algorithms for discrete case. Or we could use, for example, convex fixation if the problem is not convex, and use rounding. But at the end of the day, we always have to send back a solution to the users. And it doesn't really matter how we solve it. We need to give back a solution. And the users only have to check whether the solution is good or not. And in the context of machine learning, because we want to, sometimes consider balance between the optimization and the statistics. So sometimes these interfaces are augmented with most properties of the function. For example, we can say the function is a sum of functions, which is very typical in machine learning setting. And maybe we can also have the other properties of the function, like the function is convex, smooth, strongly convex, or we have good condition numbers, so on and so forth. And but still, the optimization researchers need to figure out how to solve it. And now when we have a sum of functions, maybe we can use some advanced version of stochastic descent like Saga, SDCA, SVRG, and more, so on and so forth. However, anyway, we have to send back the solution to the user, and the user only have to check whether the solution is good or not. So I'd like to propose some other possible interfaces, a little bit more flexible interfaces between users and optimization researchers, like this. So the user sends a function to the optimization researcher, and this function is non-convex, in most of the talk setting of this talk. Like I'm thinking mostly about non-convex functions, and maybe the first question that optimization researchers can ask is whether this function is easy or not. There might be multiple ways to interpret it. Interpreting this question, it could be this question could be interpreted as whether this function is fundamentally easy, whether we can have a polynomial time algorithm, or we could interpret it as whether we have a reasonably practical algorithm for it, or we could even interpret it as whether the trivial stochastic gradient descent can solve it. And if the answer is no, then maybe we can go back and ask, okay, this function is too hard. Can you change the function? And in typical settings, this is kind of not doable because the function itself is what we really care as the user. But for machine learning, this is somewhat, to some extent, a little bit flexible. So we can say, okay, let me try a new model and a new loss. And this is a typo last time, but I found that actually it makes some sense. So some of the audience told me, so I keep it. Because we're talking with a cat. Anyway. Okay, and suppose we figure out a new model, a new function. And okay, so I guess this is not quite for this audience, but in machine learning, we have a model, and that in supervised learning, we map x to y, and the model is a parametric function, g theta, and also we can choose the loss function in many times. So loss function and model are kind of the flexible part here. And then we find a new function, f prime, and we send it to optimization researchers. And maybe this time it's easy, and we can just use the trivial algorithm, stochastic descent, or with some momentum, tuning of learning rates, so on and so forth. So, and then we just need to send the solution back, and often we don't have to care about rounding because this new function f prime, a good solution for this f prime is suffices. And of course we have to care about other things, but in terms of solution itself, for training, we don't have to care about anything. We don't have to round. And actually, this is what happens in deep learning communities, and this is how people make progress for optimization. So, and these are very important progresses that people made in optimizations like ReLU. The introduction of ReLU significantly speed up the optimization compared to sigmoid. Over-parametrization is another powerful technique. You make the model bigger and bigger. Sometimes the model is even bigger than the number of examples, and it makes the training faster. And the batch normalization is another way to normalize the model in some way, so that the coordinates are kind of normalized across samples, and residual network is another way to change the model. So all of these don't really change the representational power of the model. They really change the optimization landscape. So it sounds like there is a possible paradigm for optimization theory in learning. So there are kind of 3 steps. So you identify a family of tractable functions, and the feasible set is the set of functions with all local minima approximately global minima. And then we can try. And another question is whether we can decide whether a function belongs to this family. Currently, we don't have that much techniques. So one of the popular techniques is kind of use some combination of linear algebra and probability in a sophisticated way. Or there are recent works that try to see whether we can use Cass-Rez formula to count how many local minima of a function has. And in this talk, I'm mostly focusing on the third bullet here, so whether we can design new objective and functions that are provably in the family F. There are some recent progresses in simplified settings. We don't know too much about it. So with Morris Hart and Ben Rett, we have tried to understand whether reparameterized or over-parameterized model can work better in the linearized setting, in linearized neural network setting. And Saudra and Carmen and Liang et al. Studied over-parameterized models and proved that over-parameterized models have better optimization landscape. In this talk, I'm going to talk about the last one, where we design new objective functions for learning one hidden neural network. And of course, just besides, so we also need to care about generalization error, but not in this talk. All right, so now let's talk about a problem that we are going to study. So we have a very, very simple setting. So assume the data x and y. X is the input, y is the label. Satisfies, it is generated by some ground truth network. So this network is just one hidden layer, so 2 matrices. So we multiply B star with x. So okay, pictorially, so we have a vector x in d dimension. We multiply matrix B star. We get some hidden variable. We pass it through some nonlinearity sigma. So sigma is you can think of it as ReLU or sigmoid, and you apply it element-wise to B star x. You get a vector, and you apply A star transpose, and you get a number y, and you add some noise. So the noise is not quite important for this talk. And a big assumption is that we assume the data from Gaussian distribution. This is a big assumption, but that's the only thing we can do. Our goal is to learn a function that predicts y given x. Although we will show that we can also recover the parameters B star and A star. All right. So, and for most of the talk, we can just think of sigma as ReLU, the max of x and 0, and for all of the experiments in the talk. But the theory also works for other activation functions. So let's start by thinking about the straightforward objective. Because we have additive noise, then it makes sense to use some L2 loss. So our prediction is just the same as our parameterized model is just the same as our assumption. So we have B and A; these are variables. So we just use the same shape as A star and B star, and so this is our prediction. And our loss is just expected square loss. This is the population loss. All right. So I guess I'm just for personal curiosity, by show of hands, how many of you think this loss function can work? Yeah. Okay, it does sound.
What sense can work?
Like it can recover the parameter A star and B star in a reasonable amount of time. Okay.
Dimensions
In a reasonable amount of time?
Like say you have an infinite number of time, like infinite amount of time, and you use a casting Vincent. So, sorry, there's this EO post question, but anyway. So I think I want to ask this because it seems that in the theoretical community, including me, I don't believe that this can be done. But most of the at least some of the researchers I talk with, doing applied research, they do believe that this can work. But the answer is that it's not going to work in the following sense. So if you look at the population risk, by not going to work, I'm just meaning that I use stochastic descent, I tune the learning rate, I decrease the learning rate carefully, and the y-axis here is the population risk. So technically, I mean the expected population risk because I take fresh samples to estimate the population risk. And the y-axis is the number of iterations. So here's the setting. So the dimension is 50. And A star is all one vector, and we assume it is known. So we don't have to even learn it. We only need to learn the matrix B. And the B star is an identity matrix, 50 by 50. So this is probably the best matrix you can hope for. And you can see the noise is 0. And we use fresh samples at every iteration. There's no generalization issue. We just do pure stochastic descent with fresh samples. And so because the noise is 0, which means that the global minimum should have population rate 0. And we can see that we cannot get it down to 0. And you can also try to see whether the parameters we learn is correct or not. Right, so the parameter, so how do we compare the parameter B with the B star, right? So what we do is that, ideally we want to make sure we want B to be a permutation of B star. So we can measure the distance between B and B star by finding the best permutation. But here we just use a surrogate loss just for computational purpose. So here the loss presented here is basically, you can think of it as if a row or column of B is epsilon far away from the natural basis in infinity norm, then the error is epsilon. So, and we can see that the error plateaus at 0.1 basically means that there's always a row or column that is 0.1 away from from any of the permutation of B star.
What optimization algorithm are you using?
We are using stochastic descent, and we decrease the learning rate, we tune the learning rate a little bit carefully. So we try to decay the learning rate after a while until it plateaus.
And is this also the case if you optimize A also?
I think so, yeah.
There is noise in the problem?
No noise. Yeah.
Do you have identifiability here?
We do have identifiability. You can see in the, it's the algorithm result we have later will show that. Yeah. All right. So some of the related work. So there are works that show that if the filters are non-overlapping, if the rows of B stars have disjoint supports, then the landscape, the straightforward objective that they showed, will work. And Yuanzhi and Yuanyang also show that initialization is sufficient. If the initialization is sufficiently close to B star in spectral norm, then it's going to work. And in our case, the bad local minima is very far from B star in spectral norm, but pretty close in infinity norm. And there are also kernel-based method, and there are also tensor decomposition method followed by local improvement algorithms. So this will give a polynomial time algorithm for the setting that I'm talking about. So our contribution is not really to propose a new polynomial time algorithm. It's more about understanding the landscape and thinking about how to change the object function. And one of the empirical solutions is that you use over-parameterization. For example, if the true dimension is 50, the dimension of the hidden vector, hidden variables is 50, and you can over-parameterize the inner tuning by a factor of 2, for example, and then the error will become much smaller. All right. So, and in this talk, we're trying to design new loss model and loss functions. But for the next slide, let me just step back a little bit to understand the straightforward object functions that I defined before a little bit better. So we're going to give an analytical formula for the object function that we defined, the L2 loss. So recall this is the setting. We have a neural network as a ground truth, and we consider L2 loss. So here is the theorem. So suppose the rows of B are unit vectors, which is reasonable assumption, and X is from spherical Gaussian. And then we have this gigantic formula for the population risk. And let me parse this for you. Let me first explain the notation. So the BIs are the rows of B, and the BI stars are the rows of B star. Okay, that's what this BI star here. And AI is the coordinate of the vector A. And sigma hat is the Hermite coefficient of sigma, the activation function sigma. So the definition is that you have HK is the normalized Hermite polynomial, and sigma hat k is just the inner product between sigma and HK. So for most of the talk, this doesn't really matter. So the only thing we know is that sigma hat k is, so they are unknown numbers. So they are properties of the activation function, and they decay reasonably fast. No, not very fast, actually. All right. So let me parse this a little bit more. So if you look at this each term for each k, this square for binom square, this is actually doing a tensor decomposition. So we have here ai star and bi star. These are ground truths, so these are kind of constant. So we have a sum of each of these ai star, bi star to the tensor power k. This is a rank 1 tensor. In order, it's an order k rank 1 tensor. So the sum is a rank m tensor. M is the dimension of the number of rows of B. So I think here. So M is the number of rows of B. So basically we are trying to decompose this rank m order k tensor by our variables. And so each of them solves the tensor decomposition problem. And so one of the original hope to use this formula is that maybe because we understand tensor decomposition better, maybe we can understand each term here better, and so that we can kind of understand the sum of them in some way. But unfortunately, if you don't do anything, this objective function is not going to be good enough. So, but still, let's look at each term just to get a little bit intuition. So f0, this is just the sum of ai star minus sum of ai. So we are trying to match the sum of ai. And f1 is the sum of ai star bi star minus the sum of ai bi Euclidean norm square. So we are trying to make sure that the linear combination of bi is the same as the linear combination of bi star. And similarly, f2 is trying to match the second moment, and f4 is trying to match the weighted fourth moment. So if you look at this term, so in some sense, this is a kind of trade-off. So the first one is a convex, but it's not enough for identifiability. The second one is not convex in both A and B, but it doesn't have spurious local minimum because it's kind of a quadratic, but it's also not enough for identifiability because we only need to match the combination of BIs. And the third one, I strongly conjecture this also has no spurious local minima, but I don't think there's an existing proof. I don't know how to prove it as well, but it doesn't sound super hard. And it's not identifiable as well because there's a rotational invariance in the BI, so you can rotate BI in a way so that you can match the second moment without recovering BI star. But the fourth one, now there's a little bit problematic because there exists a bad saddle point. All zeros, is a very bad saddle point because all the high order derivatives vanishes. So the lower order derivatives vanishes. But it's not identifiable. So if you are given the tensor sum of ai star, bi star, tensor 4, you can recover the AIs and BIs under reasonable conditions. Right. So hopefully this is a trade-off between the landscape and identifiability. So that's kind of one of the hope that we had before. And the answer is, to some extent, there's a way to make this work, and which I will show in the next slide. So here is a slightly different idea. So what we do is that now we change the model ourselves. So now in the learning, we use a different activation function gamma, even though the data are still from the same model. So what is gamma? I'll choose gamma in a moment. But still, let's just get the population risk as we have done before. So now the formula changes a little bit because we use a different activation gamma in the training. And now we have gamma hat k here and sigma hat k there. So recall that if you take gamma hat to be the same as sigma hat, then you're going to put this sigma hat k in front, and you get sigma hat k squared. So this is more or less the same formula. And so what we're going to do is that we're going to choose gamma such that gamma hat 2 is equals to sigma hat 2, and gamma hat 4 is equals to sigma hat 4. And all of the other gamma hat k, we're going to choose them to be 0. So we are free to choose this because this is in Fourier space. There's a one-to-one mapping between gamma and gamma hat. And now what happens is that if you look at any term except the second term and the fourth term, then because gamma hat is 0, then this gigantic thing is just going to be a constant because everything is fixed. A star is fixed, B star is fixed, and there's no variable. So basically what we have is that we kill all of the terms except the second term and the fourth term. We get sigma hat square times f2 plus sigma hat 4 squared times f4 plus a constant. So effectively, we are removing all of those higher order terms that seems to be a little bit difficult, and we only have the second term and the fourth term. And hope is that this will be easier. This landscape will be better because we don't have the interaction of the higher order term and the first term, and maybe it's easier to analyze. So the good news is that empirically it works, but the bad news is that still we don't know how to analyze it.
So what about the third term?
Yeah, so the good question. So the third term just naturally vanishes because because we are mostly thinking about ReLU, and for ReLU the third term is 0. Sigma hat 3 is 0. Yeah, but for other things you can probably choose the third term. It's not quite important. So so here is the empirical result. So if you do this, you tune with gamma, and the data is from sigma. And you can see that maybe the most important thing here, the left-hand side, I take f gamma minus the global minimum, because now the global minimum is not 0 anymore, and it does converge to the global minimum. And in terms of parameter error, to measure the same way as I described before, you have some heuristic way to match find the best permutation, and you measure the error, and it does converge to 0. So the same setting as before. So any questions so far? All right. So I guess I still have 5 minutes. So yes, so let's briefly discuss about the proof of non-convex algorithms. I'm a theoretician, partly a theoretician, so I still care about the approval algorithms. So how do we do that? So let's take a step back to think a little bit about what we did with the previous 2 cases. So in some sense, the key lemma that we were using to prove those to get the analytical formula for the population loss was something like this. So you take the expectation of the data y times some function of x and b. So and this expectation have analytical formula just because hk is the Hermite polynomial and the x is Gaussian, so you have some nice properties about them. So and you get something like this. The exact detail doesn't really matter. So but the thing is that we have a sum of some weighted sum of some power of the inner product between bi star and bj star and bi. And you can extend this formula a little bit and get something like, this doesn't have to be power for any polynomial here. If you replace the kth power by a polynomial, you can find another function phi p so that this formula is true. So in some sense, what I'm saying is that if you have something like this in mind, if you want to optimize this, then you can estimate at least this objective function. This function depends on b star, so you have to estimate from the data, and you can estimate using the samples. So, and you can also make this more complicated, saying you have 2 variables here, and they are there's a polynomial of the inner product between bj star and bi and bj star and bk, and you can still estimate it with from the samples. Right. So so that basically the catch is that we have some kind of family of functions that we know how to estimate using the samples, and we want to choose one function that does the job. So this is the function that we finally choose. It's a little bit complicated. The exact formula doesn't really matter for this talk, because I won't really have time to get into details. So this is degree, kind of degree 4 polynomial of b, the variable b, and is this is some polynomial of bi star times bj and bi star times bk, and we also add some term here to make things work, So and there's also a constraint that the bi is 1. So maybe before parsing this in more detail, so let me just tell you the theorem. So we assume that ai star is larger than 0. This is a crucial assumption for the theorem to work. And the b star is orthogonal, but this is not crucial. We can make it relax that assumption. So we have several things about this function. So GB, as we discussed, this can be estimated by samples. That's kind of what we discussed in the previous slide. So you can design some function that only depends on the variable and the data, so that the inner product of that function with y is GB. And also a global minimum of G is equals to b star up to permutation and scaling of the rows. So this can be seen more or less from here. So basically the only way to make this small is to choose B to be a permutation of B star. Because if that's the case, then this first term will be 0 because Bi star Bj and Bi star Bk, one of them has to be 0 if J is not equals to K. And B is just a permutation of Bi. Bj is a permutation of Bj star, then this has to be 0. And all the local minima of G are global minima. This is much more technical to prove. But in some sense, there are not so much magic here because the object function is inspired by one of the previous work by Rong-Ge et al., which proved the case when mu is 0 and AI stars are all 1. So we mostly just simplified the proof a little bit and then extended to this more complete version because we have the AI star is we don't want to assume AI stars to be all 1. So. But in some sense, they're not. This is most technical part of the paper, but there are not too much new things provided here. So the proofs are more or less standard. It's a little bit involved, but how do you prove all local minima global? What you do is you compute. You try to compute all the saddle points and all the critical points, and at least you get some properties of the critical points, and then you plug in those properties into the Hessian and see which one can survive, and you get all the local minima, and there happens to be global minimum. Right. So and this can be extended to non-singular B stars, but the limitation is that we can only deal with the case when B star is maps from higher dimension to lower dimension, which means that the hidden variable dimension has to be lower than the data dimension. All right. So, and now it starts to work, with the theorem, and also it works empirically. So I think the most important thing is the right-hand side. So in the parameter space, we can see that the error converges to 0. With a little bit hesitation, I guess. I guess what happens here is that. You have to break ties in some way so that in this metric it can go up because you have to break ties in some way. So the metric that we're using is that we want to look at the whether each row or each column is close to a natural basis. But in the training, what happens is that some of the column has to really be very close to 0 first, and then kind of close to uniform first, and then go to one of the natural bases. That's probably what happens. All right, so, and one of the caveats about the experiment is that it requires much larger batch size and training data sets. So part of the reason, I think, is that we kill too much information by kind of killing all of those high-order terms. And those high-order terms do have some useful information, but we are not using them. So the last slide. So as a conclusion, so we design new models and objectives. So we want to design new models and objectives with good landscape properties. And this paper takes one of the first steps for simplified neural networks. And some open questions. As I mentioned before, so sample efficiency is one of the drawbacks of this idea. So we need more samples to train a network compared to the straightforward objective, even though the straightforward objective doesn't converge to a perfect solution, but it does require much less samples. And the best empirical way to do it seems to be that you use ReLU, so you use absolute value for training ReLU. Basically, what this corresponds to is that you don't kill all of those high-order terms, but you only kill the first term, so F1. So you have a sum of Fk's, and you only remove F1, and then the activation function becomes ReLU. And this is the most sample efficient way that we found empirically, but maybe there are better ways. And of course, can we do beyond Gaussian inputs? Our current technique cannot do that, but maybe some of the related techniques can be useful. And another question is whether we can understand overparametrization, which is another way to simply make the experiment work. And finally, I guess we are also looking for more techniques for analyzing optimization landscape. And some of the difficulty here is that we don't know how to analyze the optimization landscape, so that we have to shoot for a different objective that can be analyzable. Thank you.
Okay, just a quick question.
So if I understand correctly, I mean, this works essentially because you know the input distribution. And you
Yes.
can so how brittle or how robust is this if you put a distribution which is epsilon close to Gaussian?
If the distribution is not Gaussian?
Is close to Gaussian. Somehow.
So if it's close to Gaussian, so actually,
Even empirically, I mean, do you see that somehow?
We didn't try it empirically, and I suspect that I discussed like 3 ways to do it. One is the way that doesn't work, and the other way is that it works, but we don't know how to prove. I think that one probably is reasonably robust to perturbations in the input, and the last one that we can analyze, probably not very robust. Or maybe it should be robust a little bit, but not very well.
But you use Hermite polynomials because your data is Gaussian, right? So
Yeah.
if you switch orthogonal polynomials, wouldn't you get something equivalent for a different kernel? Yeah, of course. It's just if you want something else, if you want to change assumption, that's it.
Yes, we thought about it a little bit, but I think there are some technical issues with doing that, but I'm not saying it's impossible. We didn't try very hard. Yeah.
Beyond the analysis, there is some universality there. That whatever the distribution you put in, the landscape should look the same. But your techniques won't work, but it doesn't mean it's not going to be true.
That's part of the hope. I don't know whether that's, I think it should be the case, to some extent. But our analysis techniques, at least for now, is very heavily using the Gaussian input. We hope that it can be, yes, I agree, yeah.
Okay, thanks.